Okay, so we're on molar volume. So the volume of a mole is called its molar volume. So this is going to be the space that a mole occupies. So whatever the particles occupy, a mole of particles, that's molar volume. And it's determined by size and spacing of particles. So if there's a lot of space between the particles, if the particles are relatively large, obviously your molar volume would be larger. And then when we're talking about temperature, a temperature increasing is going to cause the particles to move faster. They'll collide with each other with more force, which will cause them to spread apart. So that means at higher temperature, you would expect the molar volume to be greater. Okay, and let's take a look at the molar volume of gases. So let's move this down here. Okay. In the early 1800s, there was a French chemist, Joseph Gay-Lussac, that found that gases that are measured at the same temperature and pressure will react in whole number volume ratios. So what that means is if I have a chemical equation like hydrogen gas is combining with oxygen gas, and it's going to make water vapor, we're going to end up having 2 volumes of hydrogen gas reacting with 1 volume of oxygen gas to produce 2 volumes of water vapor. So this is what he noticed, okay? And using this information, there was an Italian chemist by the name of Avogadro, and he hypothesized that equal volumes of different gases at the same temperature and pressure have the same number of particles. And today we call this Avogadro's hypothesis. Okay. Now, I can take this concept one step further, and I can define a mole of any gas at 0 degrees Celsius and 101.3 kilopascals. And I can tell you that it always occupies the same volume, which is 22.4 liters. Now, this concept is known as the molar volume of gas at STP. So let me explain. This temperature and pressure are defined as standard temperature and pressure. I would expect you to know that standard temperature and pressure is abbreviated STP. I would also expect you to know that STP is this temperature and pressure. Remember, if you add 273 to degrees Celsius, you're going to get Kelvin. So that means 0 degrees Celsius is 273 Kelvin. So those are the same thing. Also, we will be talking about this in a later chapter, but kilopascals can be converted to 8 atmospheres, which is ATM. 101.3 kilopascals is the same thing as 1 ATM. So I just want to make sure that you understand that I could say 273 Kelvin or 1 ATM would also be STP. Okay, so as long as I'm at that temperature and pressure, any gas, as long as I have a mole of it, will occupy 22.4 liters. So I will give you this on a test or on a quiz. And you can use this to convert between moles and liters when you're at standard temperature and pressure. Okay, so let's take a look at the next page. And this entire section is essentially using this concept to do mole conversions or unit conversions. Okay, so on the next page, they show you how you can write that equivalence statement, a mole is 22.4 liters, as a fraction, depending upon your needs, so 22.4 on top or on the bottom. Okay, so they also give you this diagram, which shows you that if you're looking to convert between moles and liters of something, you can either multiply by 1 mole over liter when converting liters to moles, or converting moles to liters, multiply by so many liters per moles. Now, this question mark that's right here, this question mark will be 22.4 as long as we are at STP. Okay. Sometimes they'll give you the molar volume of something in a problem, and you would use that to convert between the two different units, but most of the time they don't. Okay. So here what they're showing you is that they want to know the volume of 1.3 moles of NO2. Notice they said at STP. Okay, so you put what you're given here, and then your moles of NO2 goes on the diagonal, and then you're going to liters. That's why you put 22.4 on the top, so these would cancel. Multiply across, and you'll get 29 liters of NO2. So this right here is that molar volume at STP that you can use, okay? All right, now let's take a look at the next page. All right, since this is pretty straightforward, what I'm going to have you do is I want you to do numbers 1 and 2 with the person sitting next to you, and let's see what you guys come up with.
We have
Okay, so 1.33 moles of O2. They told us we're at STP, so you can use 22.4 liters of O2 per mole. These will cancel. Did you guys get 29.8? Okay, and then for the second one, we've got 9.5 liters of SO2. They told us we're at STP, so you can use 22.4 liters. Did you guys get 0.42? Perfect, okay. So the first two problems mentioned that we're at STP, therefore we were able to use 22.4 liters per mole. However, on number 3, they gave us the molar volume of quartz. They didn't tell us anywhere in the problem that we're at STP, so we're going to use the molar volume given to solve for volume, and we're converting moles over to centimeters cubed, because centimeters cubed is the unit for volume. So 0.39 moles of silicon dioxide, and then 22.8 centimeters cubed per mole. This will cancel, and then you will end up getting 8.9 centimeters cubed. Good? Okay. Now, we're incorporating 22.4 liters into conversions and all of the other type of conversions that we learned in the previous 2 sections. Okay, so the possibilities here are kind of endless, and what I'm going to do is I'll give you a couple of math setups just to give you an idea of the possibilities, but just keep in mind I'm not giving you every single math setup that there is, because this is basically unit canceling. So let's come down here and let's add something to this wheel model. So we learned previously that we can convert grams into moles by using the molar mass of something, right? So if you're converting grams to moles, then that means you would be dividing by the molar mass. If you convert moles into a number of items, so this is things like atoms or ions or formula units or molecules, that means that here we would be multiplying by Avogadro's number as well. Now, we also know that we can convert moles over to liters of something, and if you're at STP, you would multiply by 22.4 liters per mole, okay? Obviously, if we were going in the opposite directions, we would be dividing by those things, okay? So if I wanted to start with atoms, and I wanted to go to liters, and I was at STP, I could convert atoms to moles by dividing by Avogadro's number, and then I could convert moles over to liters by multiplying by 22.4. You get the idea, yes? Okay, now all of these math setups are already in the chapter review packet, which I'm having copied for you right now. So let's take a look at a couple of sample problems before we do practice. So let's go to the next page, and let's just take a look here at what they've done. So here it says the gas in neon signs is at extremely low pressure. How many neon atoms are present in a sign that has 75 mils of neon gas at a molar volume that's 100 times greater than the molar volume at STP? Okay, so 75 milliliters is the same thing as 0.075 liters. It's a one-step metric conversion. And since they told us that it's 100 times greater than the molar volume at STP, we're going to use 2,240 liters, which is what they've done right here. So liters gets converted to moles, and then moles gets converted to atoms because atoms is a thing or an item. So here you'll notice they're multiplying by Avogadro's number. 2 sig figs is what we started with, and we're ending with 2 sig figs here, okay? If you take a look at the next sample problem, down here. Here it says natural gas is used to heat homes and may fuel the Bunsen burner in the lab. Natural gas consists of methane. What is the mass of 8 liters of methane at STP? So liters can get converted to moles using 22.4, and then moles can get converted to grams using the molar mass. Okay, let's turn to the next page. Let's take a look at one more sample problem. Here it says people often refer to the amount of CO2 produced as the carbon footprint. They want to know the volume of CO2 at STP that contains 0.2 grams of carbon. So carbon is in CO2. So we're going to convert carbon over to moles of carbon using the molar mass. And then this right here is a mole ratio within the formula. So in 1 carbon dioxide, there's 1 carbon, and then they're converting moles of carbon to liters of carbon using 22.4 because they told us that we're at STP. Okay, so let's take a look at the practice problems at the bottom of the page. H2S gas is released from rotten eggs. What volume of H2S gas at STP contains 17 grams of H2S. So we start with 17 grams. If I'm converting grams to moles, then what would I be putting on the bottom in front of grams? Right here.
Molar mass.
Molar mass, yeah. So we're going to need that new periodic table, right, that you have. We're going to have 2 hydrogens and 1 sulfur. We're going to add those together. So this is going to be 34.09. Okay, so now we've canceled out the grams of H2S. And then we're looking for the volume of H2S. So we're automatically solving for liters because they didn't give us another unit for volume, and they mentioned that we're at STP. So we put the number 1 next to moles and the 22.4 next to liters. So now these 2 units will cancel, okay? So in your calculator, it's 17 divided by 34.09 times 22.4. You should get 11 liters of H2S, okay?